What if humanity isn't the first civilization on Earth? It's a question that shakes the foundations of everything we believe about our history and our place in the universe. Could there have been another intelligent species, born not among the stars, but right here on our planet, that rose, thrived, and vanished long before us, leaving no trace but whispers buried beneath eons of rock and time? When we talk about civilization, we are not simply referring to the presence of life, but to something far more complex, a self-aware species that builds, organizes, and communicates in ways that shape the world around it. Civilization means structure. Cities rising from the ground, systems of writing and symbols to record knowledge, tools that extend our physical and intellectual reach, and art that expresses the inner landscapes of consciousness. It is the collective manifestation of intelligence acting with purpose, imagination, and continuity. It's the story of beings who not only survive, but seek to understand their existence, to leave behind a legacy that says, "We were here." When we study the long sweep of human history, we see this process unfold again and again. The Sumerians with their cuneiform tablets, the Egyptians with their monumental architecture and cosmic mathematics, the Maya charting the heavens, the Greeks shaping philosophy and science. Yet even among these examples, we realize how fragile and temporary a civilization truly is. Whole empires can rise and vanish within centuries, their greatest achievements reduced to dust. Now imagine extending that fragility across millions, even hundreds of millions of years. How much of our present world would survive that unimaginable span of time? Perhaps almost nothing. It's here that our definition of civilization begins to expand beyond human boundaries. The question before us isn't about aliens visiting from distant galaxies or advanced extraterrestrial beings guiding our ancestors, though such ideas capture the imagination of popular culture. What we are exploring is subtler, more grounded, and in many ways more profound. The possibility that intelligent life may have emerged right here on Earth long before humanity, evolved entirely from terrestrial origins, and disappeared without leaving a clear trace for us to find. This idea forces us to separate civilization from humanity. Civilization in this context is not a uniquely human achievement. It's a potential pattern in the story of life. Just as gravity draws matter into stars, perhaps intelligence draws life towards structure and society. And if intelligence is a repeating feature of evolution, something that nature tries again and again under the right conditions, then it's conceivable that we are merely the latest iteration of a process billions of years in the making. To even entertain this thought, we must recognize how narrow our perspective truly is. Human civilization covers a blink of geological time. We measure our recorded history in thousands of years, but Earth measures its history in billions. There's an incomprehensible gap between those numbers. Enough time for continents to drift apart, for entire mountain ranges to rise and erode away, for oceans to vanish and reform. In that vast ocean of time, could there have been other intelligent species that experienced their own golden ages before fading into extinction? Perhaps they were not human-like at all, maybe reptilian, avian, or even aquatic, inhabiting environments that left few geological traces. It's easy to dismiss the idea as pure speculation, but when you start to look deeper into what we know about Earth's history, the question becomes less about possibility and more about evidence, or rather, the absence of it. We define civilization through its artifacts, tools, art, architecture, and technology. But these are fragile things. Stone endures, yes, but metals corrode, glass disintegrates, and plastics, though durable in the short term, would eventually break down under heat, pressure, and chemical transformation over millions of years. Even entire cities would not last. If humanity disappeared today, how long would it take before every visible sign of us vanished? Within a few thousand years, forests would reclaim our cities. Within millions, almost nothing would remain but subtle geochemical signatures in the sediment. And so, when we ask if another civilization could have existed before ours, we must acknowledge that time itself is the great eraser. Civilization may not leave fossils in the same way bones do. Its remnants would be subtle, hidden, encoded not in ruins, but in isotopic anomalies, unexplained chemical residues, or unnatural distributions of certain elements in ancient rock layers. These are the kinds of clues that geologists and planetary scientists look for when searching for signs of past industrial activity, even on worlds like Mars or Venus. But before we chase that evidence, we must remain clear about what this question is not. It's not about myths like Atlantis or Lemuria, nor about speculative ancient astronauts visiting primitive humanity. Those are stories born from the desire to fill historical gaps with wonder. The question we are exploring belongs instead to the realm of scientific curiosity and philosophical humility. It's about acknowledging how little we truly know about the full extent of Earth's past, and how easily the traces of an entire species could vanish beneath the cycles of plate tectonics, erosion, and biological renewal. In this light, the concept of civilization becomes both humbling and universal. If intelligence is a natural outcome of evolution, and civilization the expression of that intelligence, then it's not unimaginable that others might have walked this same path before us, only to be swallowed by the shifting crust and deep time of the planet itself. The implications are staggering. We may not just be exploring the history of humanity, but the history of intelligence as a repeating phenomenon within Earth's biosphere. This redefinition widens our lens from archaeology to astrobiology, from the ruins of Mesopotamia to the sedimentary mysteries locked in Earth's crust. Civilization ceases to be a purely human story and becomes a planetary pattern, one that may have unfolded long before we arrived.
As we hold this thought, the next question naturally arises. If such civilizations did exist, why can't we find any trace of them? Why does the planet seem silent about its own possible ancient intelligences? To answer that, we have to look not at archaeology, but at the Earth itself, its deep, shifting, endlessly recycled surface. Because to understand how traces vanish, we must first understand time on a geological scale. When we begin to think in geological time, our ordinary sense of history dissolves. The human mind is built to understand centuries, perhaps millennia, but not billions of years. The Earth itself, however, is ancient beyond imagination, a planet that has existed for roughly 4.54 billion years. To comprehend that number, we must slow our thoughts, stretch our sense of scale, and recognize how small a fraction of that story belongs to us. If Earth's entire history were compressed into a single 24-hour day, the first multicellular life would appear around 8 o'clock in the evening. Dinosaurs would rule the world at 10:30 p.m., and all of recorded human civilization would fit inside the final heartbeat before midnight. Not even a second, just the brief flicker of a candle before the clock strikes 12. During that immense stretch of time, continents have formed, collided, and broken apart more than once. The face of the planet has changed so completely that no map from one era could recognize the next. Entire mountain ranges have been razed and worn down to sand. Oceans have opened, swallowed continents, and then retreated, leaving behind layered sediments that hold whispers of vanished worlds. If any civilization had existed in one of those remote epochs, the geological forces of the planet would have buried, crushed, and melted its traces long ago. What survives from ancient Earth are not monuments or cities, but patterns in stone, the chemical ghosts of life and death recorded in the language of minerals. The first half-billion years of Earth's history were violent and chaotic. The young planet, still forming, was bombarded by countless asteroids. Volcanic seas of magma covered its surface, and the atmosphere was toxic, dense with carbon dioxide and ammonia. Then, somewhere within that inferno, life began. Not as organisms we'd recognize, but as microscopic chemistry, clinging to stability in an unstable world. For billions of years, life remained simple: bacteria, algae, and microbial mats spreading across shallow seas. The fossil record tells a story of patience. Evolution moves slowly when the conditions are harsh, but every so often, an environmental catastrophe resets the game. A mass extinction, a burst of oxygen, a supervolcanic winter, an asteroid strike. Each event wipes the board clean, erasing the dominant forms of life and opening ecological space for new experiments in biology. If intelligence and civilization depend on opportunity, on long stretches of environmental stability, then it's not impossible to imagine that such opportunities may have occurred before. Consider the Cambrian explosion about 540 million years ago, when complex life erupted in every direction, filling the oceans with forms that look almost alien. Trilobites with crystalline eyes, early predators with rotating mouths, soft-bodied creatures that defy modern classification. Among them, countless evolutionary lineages emerged and disappeared without leaving descendants. If one of those lineages had developed even a primitive intelligence, its traces would be almost entirely lost today. 100 million years is enough for continents to subduct into the mantle. 500 million ensures total erasure. Humanity's place on this timeline is fragile. Anatomically modern humans appeared about 300,000 years ago, a blink of an eye in planetary history. Agriculture, cities, and writing have existed for perhaps 10,000. Our industrial age, the era of steel, satellites, and atomic energy, has lasted little more than 2 centuries. Against 4.5 billion years, we are less than a spark in a storm. If civilization vanished tomorrow, within a few million years, tectonic forces would erase nearly every trace. Even the tallest skyscrapers would crumble and be buried. Only the clues remaining would be subtle. A thin layer of synthetic chemicals, traces of plastic polymers turned into rock, or unusual isotope ratios in sediment where nuclear tests left their mark. A visiting geologist millions of years in the future might find that layer and wonder, briefly, whether some strange species once reshaped the planet before vanishing into extinction. When scientists look at the deep past, they find that the Earth itself is a master of recycling. Through a process called plate tectonics, the crust is constantly renewed. Ocean floors, for example, are young compared with continents. No piece of oceanic crust older than about 200 million years remains at the surface. Everything older has been dragged downward into the mantle, melted, and reborn as new rock. That means that any coastal civilization, any city built along the sea, which is where humans most often build, would be obliterated on that timescale. Even continental interiors are not safe. Erosion grinds mountains into dust, glaciers scrape valleys clean, and rivers rearrange landscapes. Given enough time, every trace of human construction would be transformed into anonymous minerals. This understanding reframes the question entirely. If humans can disappear so easily in the geological record, then how can we confidently say that no intelligent species came before us? We rely on fossils, artifacts, and sediments to read history, but those archives are fragmentary. Less than 1% of all species that ever lived are represented in the fossil record. The rest are simply gone, their existence erased by pressure and time. So when we say that no earlier civilization existed, what we truly mean is that we have not yet found evidence, and that the odds of that evidence surviving are vanishingly small.
The geological timescale reminds us of our ignorance. It divides Earth's history into eons, eras, periods, and epochs. Names like the Archean, the Proterozoic, the Paleozoic, the Mesozoic, the Cenozoic. Each boundary marks a transformation, mass extinctions, sudden radiations of life, shifts in atmosphere and climate. When viewed from this grand perspective, the rise of humans is not a culmination, but a continuation, one more fleeting expression of nature's creativity. Civilizations could have come and gone in earlier eons, erased not because they were insignificant, but because the planet is endlessly dynamic. Standing on the rim of a canyon, looking down at layered rocks that span hundreds of millions of years, one can feel this truth in silence. Every band of color is a page in Earth's memory, yet entire epochs are missing, worn away or hidden beneath others. The story of our planet is full of blank chapters, voids that stretch for hundreds of millions of years. Within those empty pages, anything could have happened. And so, as we peer deeper into those forgotten ages, the question becomes less of fantasy and more of curiosity. If an ancient civilization did rise and fall in one of those missing intervals, would we even know it? To answer that, we must confront the planet's most ruthless trait, its ability to erase itself.
Erosion, tectonics, and the recycling of the crust act as nature's delete key, wiping the geological slate clean again and again. To grasp how total that erasure can be, we must explore the problem of evidence itself, what survives, what doesn't, and why even the greatest civilizations could vanish without a trace. The problem with evidence is, in many ways, the heart of this mystery. Everything that defines a civilization, its buildings, its art, its machines, its written language, depends on materials that the Earth itself relentlessly consumes. The planet is not a static museum, but a living engine of change, constantly reshaping, renewing, and erasing its surface. Mountains rise and crumble, oceans expand and shrink, continents drift across the globe like slow-moving ships of stone. Over millions of years, even the most monumental structures would vanish not through some dramatic catastrophe, but through the quiet, unstoppable processes of geology. Erosion is the first and most familiar of these destroyers. It's the patient sculptor that never rests. Every drop of rain, every gust of wind, every freeze and thaw works to grind the landscape down. The tallest mountains on Earth, the Himalayas, are still growing due to tectonic uplift, yet at the same time they are being worn away by rivers and glaciers. Over millions of years, erosion flattens everything. A city built of stone and steel would crumble to rubble within tens of thousands of years, its remains buried beneath silt and vegetation. Fast forward another few million, and even that rubble would be compressed into sedimentary rock, its recognizable shapes crushed into unremarkable layers of quartz, clay, and carbonate. Then comes tectonic activity, the planet's slow but immense rearrangement of its outer shell. The continents ride on plates that drift atop a molten mantle, colliding and pulling apart in cycles that take hundreds of millions of years. When plates converge, mountain ranges form. When they diverge, new ocean basins open. The surface of the Earth is recycled in this way. Old crust sinks back into the mantle, where it melts and reemerges as new rock elsewhere. This process, known as subduction, is perhaps the most efficient eraser imaginable. It ensures that no part of the planet's crust older than about 200 million years survives on the ocean floor. Anything built there, any trace of coastal or marine civilizations, would be dragged down, melted, and obliterated. Even the continents, which endure longer, are not immune. They too are reshaped by earthquakes, volcanic activity, and the slow bending and fracturing of rock under the weight of geologic stress. The forces at work are unimaginable in scale, but subtle in speed. A city might stand for 1,000 years before decay, but the Earth moves to a rhythm measured in millions. Entire mountain ranges can be erased in the time it takes for a star to orbit the galaxy once. If a civilization rose during one of those cycles, say 100 million years ago, the odds of its remnants surviving to the present would be almost zero.
We can look at our own world to understand this better. Think of the pyramids of Giza, some of humanity's most enduring monuments. They are made of stone, built to last for eternity. Yet even they are slowly dissolving under the assault of time, weather, and sand. If humans disappear today, the pyramids might endure for another few tens of thousands of years before crumbling completely. Steel bridges would rust and collapse in a few centuries. Glass towers would shatter and vanish into dust, and concrete would slowly break down under chemical attack. Nature would reclaim everything. Forests would spread across cities, rivers would carve through highways, and in less than 10 million years, a blink in geological time, nearly every trace of us would be gone. Imagine that billion-year horizon. Picture the Earth 1 billion years from now. The continents unrecognizable, the oceans rearranged, mountain chains replaced by new ones, and the atmosphere itself altered by biological and geological evolution. Our planet would bear no visible sign that we ever existed. The very crust on which our cities stand would have been subducted into the mantle and reformed as volcanic rock, the evidence of our existence mixed into the planet's molten heart. Only a trained geologist, studying strange chemical fingerprints in ancient strata, might suspect that something unusual once happened here. Perhaps an unexplained spike in carbon, a sudden abundance of synthetic compounds, or isotopic ratios that suggest artificial manipulation. But even those signs would be subtle, difficult to distinguish from natural processes, and eventually lost to the planet's endless cycles. It's humbling to realize that our global civilization, with all its complexity and ambition, is ephemeral on a planetary scale. We often imagine our creations as permanent: the skyscrapers that touch the clouds, the satellites that circle the Earth, the roads that stretch across continents. Yet they are temporary ripples on a surface that constantly shifts and renews itself. From the perspective of deep time, humanity's entire existence is like writing in sand at the edge of the tide. No matter how carefully the letters are drawn, the waves will come. Even fossils, which seem eternal, are selective survivors. They require precise conditions to form: rapid burial, mineral-rich water, and the absence of oxygen. Most organisms, even entire species, leave no fossil record at all. Soft-bodied creatures, which may have dominated life for billions of years, are almost invisible in the geological archive. Now imagine trying to fossilize a city, a structure of metal, glass, and synthetic material in such conditions. The probability is astronomically low. And even if a fragment survived, would a future civilization recognize it for what it was? Or would it appear to them as nothing more than a strange mineral inclusion, a natural oddity in the rock? This realization leads us to a kind of paradox. The longer a planet remains geologically active, which is necessary for life to thrive, the better it becomes at erasing its own history. Mars, by contrast, is geologically dead. Its surface, scarred and ancient, preserves features billions of years old. But Earth's vibrancy, the same dynamism that supports life, also ensures that its deep past remains hidden. The more alive a world is, the less it remembers. So when we look around and see no evidence of pre-human civilizations, perhaps we should not take that as proof that they never existed, but as a reminder of how efficient Earth's memory is at forgetting. After all, we have been here for such a brief moment, and already nature is reclaiming the edges of our cities. In a few thousand years without maintenance, our power plant and skyscrapers would collapse. In a few million, the evidence of our existence would be reduced to faint chemical echoes. In a billion, there would be nothing left at all. And yet, scientists have begun to ask, if such a civilization had existed millions of years ago, would we be able to detect even the faintest trace of it? Is there a scientific framework for exploring that possibility? A way to look for industrial or technological activity in the geological record, even when no direct artifacts survive? In recent years, one intriguing concept has emerged to explore exactly that question. It's called the Silurian Hypothesis, a thought experiment that dares to ask if Earth might once have hosted another intelligent civilization long before humans ever appeared, and if so, how we might recognize its fingerprints hidden in the rocks. The question of lost civilizations has long fascinated humanity, but for the most part it has lived at the fringes of mythology and speculation. Stories of Atlantis, Mu, or other vanished worlds. However, when professional scientists begin to seriously entertain the idea, the conversation takes on a different tone. It becomes not a matter of fantasy, but of methodology. How would we know if an advanced civilization had once existed millions of years before us? What kind of evidence would survive, and what would it look like? In 2018, two scientists, Gavin Schmidt, director of NASA's Goddard Institute for Space Studies, and astrophysicist Adam Frank from the University of Rochester, decided to formalize that question into a scientific framework. They called it the Silurian Hypothesis.
The name itself is a playful nod to science fiction. In the British television series Doctor Who, the Silurians were an ancient race of intelligent reptilian beings who ruled the Earth long before humans, retreating underground after a global catastrophe. When Schmidt and Frank borrowed that name, they did so not to suggest that such creatures literally existed, but because it captured the essence of their inquiry. Could there have been an intelligent, technologically capable species on Earth long before humans? And if so, how could we tell? Their hypothesis doesn't rely on myths or conspiracy theories. Instead, it asks a disciplined, scientific question. If an industrial civilization had arisen tens or even hundreds of millions of years ago, would there be any detectable trace left in the geological record today? The answer they found is both fascinating and unsettling. because while direct evidence like artifacts or ruins would almost certainly be gone, there might still be indirect fingerprints hidden in the chemistry of the planet itself. To explore this, Schmidt and Frank turned to the concept of the Anthropocene, the proposed geological epoch defined by humanity's impact on the Earth. If we vanished tomorrow, what markers would we leave for future geologists millions of years from now to find? The answer is subtle, but measurable. There would be spikes in carbon dioxide from fossil fuel combustion, widespread deposits of synthetic materials like plastics, isotopic changes from nuclear activity, and unusual patterns of sedimentation due to agriculture and deforestation. These signatures would form a thin but distinct layer in the sedimentary record, a permanent record of our industrial age. Now, if we flip that question around, we can ask, could a similar layer exist beneath us, laid down by a previous civilization? If we were to drill deep into ancient rock formations, say from the Paleocene or Cretaceous periods, might we find anomalous chemical signatures that suggest industrial activity long before humans existed? That's the essence of the Silurian hypothesis. It doesn't claim that such a civilization actually existed, only that we should consider how we might detect one if it had. Schmidt and Frank approached the problem with caution and rigor. They pointed out that geological processes destroy or obscure most records older than a few million years. Even so, certain geochemical traces could persist. For example, large-scale use of hydrocarbons would alter the ratio of stable carbon isotopes in sediments. Manufacturing processes might introduce synthetic compounds, unusual metals, persistent organic pollutants that don't occur naturally. Nuclear technologies could leave traces of specific isotopes with long half-lives, detectable even after eons. If we ever found such anomalies in strata predating humanity, we might have to entertain the possibility that they were not purely natural. However, the challenge is immense. Natural processes can mimic many of these effects. Massive volcanic events can produce carbon isotope shifts similar to those from industrial emissions. Meteor impacts can cause widespread fires and deposit metals in glassy spherules. Even changes in ocean chemistry or methane release from seafloors can create geochemical signatures that, at a glance, resemble the aftermath of industrial activity. To distinguish between natural and artificial causes requires extraordinary precision, and even then, the line is blurred by the complexity of Earth's systems. The Silurian hypothesis, therefore, is less a claim about what was and more a framework for understanding what might be possible. It's a thought experiment designed to test our assumptions about how civilizations leave traces and how fragile those traces are across deep time. By asking how we would recognize the remains of an ancient industrial species on Earth, we also refine our search for technological civilizations elsewhere in the universe. In essence, it's a mirror held up to our own future and our own impermanence. Schmidt and Frank concluded that while there's no current evidence for a pre-human civilization, the absence of evidence isn't the same as evidence of absence. The Earth's geological record is incomplete and biased toward the recent. The deeper one digs into time, the sparser the clues become. Entire eras, spanning hundreds of millions of years, are represented only by a handful of rock layers, often distorted, metamorphosed, or lost. If an industrial civilization had lasted, say, 50,000 years, as ours might, and ended 100 million years ago, the chances of finding direct evidence would be practically zero. And yet, even as the hypothetical, the Silurian idea is profoundly humbling. It reminds us that we too are temporary, that all our science and architecture could vanish as completely as the bones of forgotten species. The Earth is not a keeper of records. It is an artist that endlessly paints over its own canvas. If another intelligence once lived here, we may never know it, not because they weren't real, but because time itself is the great eraser.
Still, the Silurian hypothesis opens a new door in our imagination. It bridges the human and the cosmic, connecting our curiosity about ancient Earth with our search for life beyond it. For if we can ask whether civilizations have risen and fallen on our own planet, then it's only natural to wonder, where did life itself begin? Did intelligence first emerge here, or are we part of something older, seeded from elsewhere in the cosmos? A biological heritage shared across the stars. That question carries us from the depths of geological time to the vastness of space, into an idea as old as philosophy and as modern as astrobiology. The notion that life, perhaps even intelligence, might travel between worlds. It's time to explore that cosmic possibility, known as the theory of panspermia. When we reach the limits of Earth's memory, when every trace of potential ancient civilizations is swallowed by the churning crust, the natural question becomes even larger. If time and geology erase everything, then perhaps the roots of our story reach beyond the Earth itself. Maybe our planet is not the cradle of life, but merely one of its many nurseries. The thought is both startling and strangely comforting. Because if we cannot find the beginnings of civilization here, perhaps that's because life, the raw material of civilization, did not begin here at all. This is where gaze lifts from the ancient stones of Earth to the vast sweep of the cosmos, and we encounter an idea both ancient and modern, panspermia. The word comes from Greek, pan meaning all, and sperma meaning seed. The hypothesis suggests that life, or at least the building blocks of it, might be a universal phenomenon, spreading through space from planet to planet, carried on meteors, comets, and cosmic dust. In this view, Earth was not the singular birthplace of life, but one of many worlds seeded by biological material drifting through the galaxy. The transition from geological speculation to cosmic speculation feels natural, even inevitable. After all, if we are contemplating civilizations that may have risen and fallen unseen on Earth, why stop at our planet? The universe is vast, ancient, and filled with countless opportunities for life to emerge. And if life can travel, if it can endure the cold, radiation, and emptiness of space, then perhaps intelligence too has deeper, older roots than we imagine. Humanity might not only be the latest civilization on Earth, but a branch on an ancient interplanetary tree of life. The idea of panspermia doesn't claim that fully formed organisms drift through space like spores in the wind. Rather, it proposes that life's essential ingredients, complex organic molecules, amino acids, and perhaps hardy microbial life, can be transported across astronomical distances. The universe, it suggests, is not a sterile void, but a dynamic environment rich in chemistry. Every star system becomes a potential laboratory, every asteroid a messenger carrying the seeds of biology. When one of those cosmic messengers strikes a young, fertile world, a planet with liquid water and a stable atmosphere, those seeds might take root, adapt, and evolve. And if that's true, then the origin of life on Earth might not mark the beginning of the story, but simply the local chapter. Life could be far older than our planet, its lineage stretching back to epochs predating the sun itself. In that case, we are inheritors of a universal process, participants in a cosmic chain reaction that has been unfolding since the earliest stars lit up the darkness. The beauty of the panspermia hypothesis lies in its ability to connect everything, geology, biology, astronomy, and philosophy, into one continuous story. It suggests that life is not an isolated accident, but an emergent feature of the universe itself. The atoms that form our bodies were forged in stars. Perhaps the molecules that animated them were born in the cold interstellar clouds that drift between those stars. When a new solar system forms, those molecules are incorporated into planets, waiting for the right conditions to awaken. Under this model, every world with water and warmth becomes a potential home for life. Not a lonely oasis, but part of a vast, interconnected web stretching across the Milky Way.
But what gives this idea scientific weight is not just its poetry. It's the evidence, slowly gathered over decades, that shows the ingredients of life are everywhere. Astronomers have detected complex organic compounds in the tails of comets, in the atmospheres of distant planets, and in the dusty regions between stars. Meteorites that have fallen to Earth contain amino acids, the very molecules used to build proteins in all known life. Even more astonishingly, we now know that microscopic organisms on Earth, extremophiles, can survive the harsh conditions of space, enduring radiation, freezing, and vacuum. Panspermia, therefore, offers an elegant bridge between worlds. It says that life may not be confined to one planet's timeline, but may instead hop from one to another, spreading like an invisible mycelial network through the galaxy. If that's true, then the seeds of our existence could have been drifting for billions of years before finding their way to Earth.
We might be part of a lineage older than the planet itself, descendants not only of terrestrial evolution, but of cosmic ancestry. This perspective reshapes everything we think we know about civilization. If life can migrate through the cosmos, then intelligence, the capacity for thought, culture, and technology might also arise repeatedly in different places and times. We might not just be asking whether other civilizations existed before us on Earth, but whether the roots of civilization reach beyond our planet entirely. Perhaps we are part of a grander story, one in which life and intelligence are not Earth's inventions, but the universe's natural expression. And yet, before we get too lost in wonder, we must remember that panspermia is not a conclusion, but a hypothesis. It's a framework for exploration, a reminder that the boundary between Earth and space is more porous than we once thought. The materials that form our world came from the stars, and perhaps so did the spark that brought those materials to life. As we move forward, the next step is to understand how panspermia might actually work. How can life, so fragile and dependent on precise conditions, survive the cold vacuum of space? What physical processes could allow microbes or organic molecules to travel across light years and still remain viable? These questions bring us to the scientific core of the theory, a closer look at how the seeds of life might truly journey between worlds. Panspermia at its simplest is the idea that life can travel through space like seeds on the wind, landing in places where it can grow. Instead of imagining fully formed organisms crossing vast distances, think of it as tiny parcels of life, microbes, bacteria, or even just the basic organic molecules that make life possible, hitching a ride on asteroids, comets, or dust particles. These space travelers can survive the harsh conditions of the cosmos, extreme cold, intense radiation, and the vacuum of space, protected inside rocky fragments or encased in resilient spores. When these celestial messengers crash onto a young planet with water, warmth, and a suitable atmosphere, the seeds they carry may begin to grow and multiply, eventually evolving into complex forms of life we see on Earth today. The process can be visualized as a cosmic relay. A meteor impact on one planet, for example, can eject rock fragments into space, carrying with them hardy microbial life. These fragments drift through the void for potentially millions of years before being captured by the gravity of another world. If that world has the right conditions, perhaps shallow oceans, protective soils, or sheltered environments, the microbes awaken and start the process of colonization. Over time, these microscopic pioneers can evolve, adapting to the planet's environment, and given enough time, producing the rich diversity of life we see on Earth today. Panspermia doesn't require intelligent intervention or miracles. It works through entirely natural processes. The universe, with its billions of stars and countless planets, offers countless opportunities for life to spread. A single comet or asteroid strike might be enough to transport life from one corner of the galaxy to another, linking worlds in a chain of biological inheritance. In this sense, Earth could be part of a much larger network of life, a single node in a web that stretches across light years. The concept also explains how life could appear on multiple planets independently, without requiring the improbable event of spontaneous generation on each one. Life, or at least its building blocks, might simply be moving around the cosmos, waiting for the right conditions to take root. This makes the story of life less about accidents confined to one planet, and more about a universal principle. Given the right materials and conditions, life emerges, spreads, and evolves. By thinking of life as seeds traveling through space, panspermia reframes our perspective. Earth is not an isolated experiment. It's part of a cosmic ecosystem, a beneficiary of materials and life that may have originated millions of light years away. And if life can travel in this way, then the possibilities for ancient civilizations rise as well. Any planet seeded early in this process could, given millions or billions of years, produce intelligent beings capable of building societies, technology, and perhaps even interplanetary communication. In other words, panspermia turns the universe itself into a garden, where life sprouts wherever the soil is suitable, and the seeds may come from far beyond the borders of a single planet. It's a humbling, exhilarating way to think about our origins, not as an isolated fluke on Earth, but as the result of a chain reaction that has been unfolding across space and time for billions of years. And to understand how seriously scientists consider this, it helps to look at the history of the idea and the thinkers who championed it, the minds that first imagined life hopping across the stars. The idea that life might come from beyond Earth is far older than modern science, stretching all the way back to the earliest days of philosophical speculation. More than 2 millennia ago, the Greek philosopher Anaxagoras proposed that life might exist throughout the cosmos, and that the seeds of life could be distributed from one celestial body to another. Although his reasoning was rooted in the limited knowledge of his time, it reflected a profound recognition. Life may not be confined to our planet, and the universe itself could harbor the potential for living systems in multiple locations. Anaxagoras was one of the first to challenge the notion that Earth was unique in its ability to host life, planting the conceptual seed that centuries later would grow into the scientific idea of panspermia.
During the centuries that followed, the idea remained mostly philosophical, expressed in abstract speculation or poetry, rather than empirical research. But with the development of modern astronomy and biology, the hypothesis gained new rigor. The discovery of microscopic life, the realization that comets and asteroids carried organic compounds, and the growing understanding of planetary formation all made it increasingly plausible that life could travel through space. By the 20th century, the seeds planted by early philosophers were beginning to be nurtured by science. Two of the most influential figures in bringing panspermia to the forefront of modern scientific discourse were Fred Hoyle and Chandra Wickramasinghe. Hoyle, an English astronomer famous for his work on stellar nucleosynthesis and for coining the term Big Bang, albeit critically, approached the idea with a mix of cosmic ambition and meticulous reasoning. Alongside Wickramasinghe, he proposed that life on Earth might have been delivered from space via comets, asteroids, or interstellar dust. They argued that the building blocks of life, even microorganisms, could survive the harsh conditions of space if shielded within rock or ice. Hoyle and Wickramasinghe also suggested that many of the diseases and biological changes observed on Earth might be influenced by extraterrestrial microorganisms arriving intermittently. While this claim remains controversial, it helped to popularize the concept of panspermia as a legitimate scientific hypothesis rather than a fanciful idea. Their work underscored an essential point: life is resilient, and the universe is vast enough to provide the opportunities and mechanisms for its distribution. They moved the conversation from speculation about alien life to a framework grounded in chemistry, biology, and astrophysics, asking questions that could be tested through observation and analysis. The influence of Hoyle and Wickramasinghe expanded beyond academic papers. They inspired generations of scientists to examine meteorites, comets, and interstellar dust for organic compounds, fueling discoveries that continue to shape astrobiology today. Their ideas provided a bridge from the ancient musings of philosophers like Anaxagoras to a modern, testable hypothesis about the spread of life. In essence, they reframed our thinking. Life might not be a rare accident confined to one planet, but a natural consequence of the universe's chemistry, waiting to propagate wherever conditions permit. This historical trajectory highlights how the concept of life's cosmic origin has evolved over centuries, from a philosophical intuition in ancient Greece to a hypothesis that engages with modern astronomy, biology, and chemistry. Panspermia demonstrates the continuity of human curiosity. Each thinker, whether philosopher or scientist, was attempting to answer the same fundamental question: is life a product of Earth alone, or a cosmic phenomenon with roots that stretch across the stars? The work of Hoyle and Wickramasinghe, in particular, paved the way for the empirical investigations that followed. By studying comets and meteorites, scientists began to find tangible evidence supporting the plausibility of life's interstellar journey. These discoveries revealed that the molecules necessary for life are widespread in space,
suggesting that Earth may have been seeded naturally as part of a much larger, universe-wide process. Understanding this historical background helps us see that panspermia is not a fringe idea. It is a result of centuries of intellectual inquiry, refined by scientific evidence and informed speculation. It frames the possibility that life on Earth, and perhaps intelligence itself, may be part of a chain reaction extending far beyond our planet, one that began long before humans ever walked the Earth. And if life can travel across space and endure such extreme conditions, it brings us to a crucial question. How do we know that microbes or organic molecules could actually survive the journey? That is where the study of extremophiles and the survival capabilities of microscopic life in space provides compelling insight, demonstrating that the universe may indeed be far more hospitable to life than we once imagined. One of the strongest arguments in favor of panspermia comes not from speculation, but from observation, from the study of life here, on Earth, in places once thought utterly inhospitable. Enter extremophiles, microorganisms that thrive under conditions lethal to most forms of life. Some live in the scalding waters of hydrothermal vents at the ocean floor. Others endure the crushing pressures kilometers beneath the ice, and some survive in deserts so dry that they seem devoid of moisture. Among these organisms, scientists have found proof that life is far tougher than previously imagined, capable of enduring conditions that closely mimic the harshness of outer space. Consider the challenges of space travel. Microbes would need to survive extreme cold, vacuum, high levels of cosmic radiation, and potentially decades or even millennia trapped inside rocks or icy comets. This seems impossible for most life as we know it. But extremophiles demonstrate that survival under these conditions is not only plausible, but sometimes routine. Certain bacteria, such as Deinococcus radiodurans, can resist doses of radiation thousands of times higher than what would be lethal to humans, repairing damage to their DNA with astonishing efficiency. Others, such as Bacillus subtilis, can form spores that remain dormant for decades, even centuries, and endure desiccation, freezing, and chemical assaults. These traits make them ideal candidates for life capable of surviving interplanetary travel. Experiments in space have confirmed these possibilities. Microbes sent aboard satellites and the International Space Station have survived direct exposure to the vacuum and radiation of space. For example, in experiments like the European Space Agency's EXPOSE series, bacterial spores and lichens endured months in low Earth orbit, surviving ultraviolet radiation, cosmic rays, and extreme temperature fluctuations. Some organisms even showed the ability to resume normal biological functions upon return to Earth, proving that long-term survival beyond our planet is feasible. Even more remarkable are findings that suggest life can endure shock events, the extreme forces generated by planetary impacts. Meteorites striking a planet with enough velocity to eject rock fragments into space produce immense pressures and heat, conditions that would seem fatal to most life. Yet laboratory simulations have shown that some spores can survive shocks of several gigapascals, pressures comparable to those experienced during asteroid collisions. This means that life could realistically hitch a ride on debris ejected from one planet and potentially arrive intact on another, supporting the idea of lithopanspermia, where life hops between worlds on rocks.
The fact that Earth hosts organisms capable of such resilience gives the panspermia hypothesis a scientific backbone. Life isn't merely fragile or local. It has built-in strategies to endure extremes, strategies honed over billions of years of evolution. Microbes capable of dormancy, DNA repair, and radiation resistance illustrate that the building blocks of life are far more robust than previously assumed. If such life can survive in the harshest niches on Earth, it becomes plausible to consider that it could survive journeys across the solar system, or even between star systems, embedded in rocks, dust, or ice. This understanding also reframes our perception of space itself. Rather than an absolute void of destruction, space becomes a conduit, a medium through which life can propagate. Microbes do not need to actively travel, they simply need to endure long enough for random cosmic processes, asteroid impacts, comet collisions, planetary gravity, to transport them to suitable environments. Over millions or billions of years, these slow journeys could connect distant worlds, carrying life to planets that would have otherwise remained sterile. The survival of extremophiles also provides a bridge between the idea of cosmic seeding and the earlier notion of ancient civilizations. If life itself can endure the void of space, then its emergence is not a local accident, but part of a larger, perhaps even cosmic process. Given enough time, the life that arrives on a planet can evolve in countless directions, potentially giving rise to intelligent species capable of developing civilization. In other words, the universe not only seeds life, it sets the stage for complexity, adaptation, and eventually consciousness. And the evidence doesn't stop at microbes. Molecules essential for life, such as amino acids, sugars, and nucleobases, have been detected in meteorites and cosmic dust. But before we delve into the chemical evidence, it's essential to appreciate that life, in its most resilient form, could survive the journey itself. Extremophiles provide the living proof that the seeds of life can withstand space's hostility. Without them, panspermia would remain an elegant but purely theoretical concept. With them, it becomes scientifically plausible, a mechanism by which life could travel across the cosmos, planting the potential for future civilizations wherever conditions are right. From the extraordinary resilience of extremophiles, we now turn to the tangible evidence that supports panspermia. Meteorites and cosmic material that carry the very molecules and microstructures, suggesting that life may not have originated on Earth at all, but could have been delivered from the stars themselves. If extremophiles demonstrate that life can survive the harsh conditions of space, meteorites provide the physical evidence that such interplanetary journeys may actually occur. Meteorites are fragments of asteroids, comets, or even other planets that have survived the fiery plunge through Earth's atmosphere, delivering material from distant worlds directly to our doorstep. Among these, certain meteorites stand out because they contain compelling traces that suggest that life may have existed elsewhere, perhaps even seeding Earth with the building blocks of biology. One of the most famous examples is ALH 84001, a meteorite discovered in Antarctica in 1984 and identified as originating from Mars. This rock is estimated to be over 4 billion years old, formed during a time when Mars may have had liquid water on its surface. In 1996, a team of scientists led by David McKay at NASA announced that ALH 84001 contained microscopic structures resembling fossilized bacteria. They also identified unusual carbonate globules and chemical signatures, including magnetite crystals and polycyclic aromatic hydrocarbons, that could be interpreted as remnants of biological activity. While the findings remain debated, they sparked a worldwide conversation about the possibility that life exists, or once existed, beyond Earth. What makes ALH 84001 particularly intriguing is not just its potential microbial fossils, but its implications for panspermia. If life ever existed on Mars, then asteroid impacts could have ejected rocks containing microbes or resilient organic molecules into space. Some of these rocks, traveling across millions of kilometers, could eventually land on Earth. This mechanism, known as lithopanspermia, provides a direct pathway for life to spread between planets. ALH 84001, whether or not it contains definitive proof of past Martian life, serves as a concrete reminder that material exchange between worlds is not only possible, but inevitable on cosmic timescales. Other meteorites reinforce this possibility. Many carbonaceous chondrites, for instance, contain complex organic compounds, including amino acids, sugars, and nitrogen-containing molecules that form the backbone of DNA and RNA. The Murchison meteorite, which fell in Australia in 1969, contains more than 70 different amino acids, many of which are rare or absent on Earth. These findings indicate that the chemical precursors to life are abundant in the cosmos, easily transported across interplanetary distances. If these compounds can survive the impact of landing on a planet, they could kickstart biological processes in environments that are otherwise sterile. Meteorites like ALH 84001 also highlight the resilience required for life to traverse space. To survive ejection from one planet, a journey through the vacuum of space, and eventual atmospheric entry on another, any microbial life must withstand immense pressures, radiation, and extreme temperature fluctuations. The study of meteorites shows that this is not a hypothetical scenario. Rocks from Mars and other bodies routinely impact Earth, delivering both organic material and the potential for microbial life. Over billions of years, this process could have repeatedly seeded Earth, providing the raw ingredients for life to take hold. Importantly, meteorites do more than just suggest possibilities. They provide tangible, testable evidence. Scientists can analyze their isotopic compositions, mineral structures, and chemical signatures, searching for anomalies that indicate biological processes. While controversy remains, distinguishing between abiotic and biotic origins is extraordinarily difficult, but the presence of complex organic molecules in space rocks shows that the universe is chemically fertile. Life, in its most simple forms, may not be a unique event confined to Earth, but rather a natural outcome of cosmic chemistry.
This evidence ties directly back to the concept of panspermia. Life doesn't need to start on Earth. The seeds of biology may arrive already formed, delivered on rocks traveling millions of kilometers. Meteorites act as messengers, demonstrating that the universe has mechanisms to transfer life between planets, and perhaps even between star systems. If ALH 84001 and other meteorites once carried microbes from Mars or beyond, then Earth's biosphere may be the result of a complex chain of cosmic events, a tapestry woven from materials scattered across the solar system. Meteorites also offer an important insight into the timing and origin of life. ALH 84001 is more than 4 billion years old, a period that coincides with the earliest evidence of life on Earth. This raises tantalizing questions. Could Martian microbes transported via meteorites have contributed to the emergence of terrestrial life? Could similar processes have seeded other planets, creating a network of life throughout the solar system and beyond? While definitive answers remain elusive, the very possibility challenges the traditional view that life is a rare, isolated phenomenon. Instead, it paints a picture of a universe in which biology is inherently mobile, opportunistic, and resilient. In short, meteorites like ALH 84001 and the Murchison meteorite provide a bridge between theory and evidence. They demonstrate that the raw materials of life are not confined to Earth and that interplanetary travel of life is physically possible. These cosmic messengers make panspermia more than a philosophical idea. They show it as a mechanism that could have operated throughout Earth's history, delivering life, or its precursors, long before humans ever appeared. And if life, even in microbial form, can travel across the cosmos, then the chemical foundation for life is widespread. This brings us to a broader view of the universe, where not just microbial life, but the building blocks of biology itself are distributed on a cosmic scale. Amino acids, sugars, and nucleobases have been discovered in comets, asteroids, and interstellar clouds, hinting at a universe rich in the ingredients of life, a universe ready to seed worlds whenever the conditions are right. One of the most compelling aspects of the panspermia hypothesis is the realization that the ingredients for life are not rare anomalies confined to Earth, but instead are widely distributed throughout the cosmos. Over decades of research, astronomers, chemists, and planetary scientists have discovered that comets, asteroids, and interstellar dust clouds contain a surprising abundance of the very molecules that make life possible. Amino acids, the building blocks of proteins, along with sugars, nucleobases, and other complex organic molecules, have been detected in multiple extraterrestrial sources, suggesting that the raw materials for life are not a terrestrial accident, but a cosmic norm. For example, the Murchison meteorite, which fell in Australia in 1969, contains more than 70 different amino acids, many of which are rare or absent on Earth. These amino acids are arranged in ways that hint at chemical pathways potentially conducive to life. Similarly, comets have been found to carry not only simple molecules like water and carbon monoxide, but also more complex organics, including methanol, formaldehyde, and even glycolaldehyde, a simple sugar that can give rise to more complicated carbohydrates under the right conditions. The Rosetta mission to Comet 67P Churyumov-Gerasimenko confirmed the presence of organic molecules, revealing a complex chemical inventory that includes glycine, the simplest amino acid used in terrestrial proteins. Even interstellar space itself is rich in organics. Observations using radio telescopes have identified molecules such as formaldehyde, ethanol, and even precursors to nucleobases floating in cold, dense molecular clouds between stars. These clouds act as cosmic chemical factories, where ultraviolet radiation, cosmic rays, and shock waves catalyze reactions that build increasingly complex molecules. Over time, portions of these clouds collapse under gravity to form new stars and planetary systems, effectively delivering pre-assembled organic matter to nascent worlds. In other words, the seeds of biology can be baked into the very fabric of star-forming regions, ready to be incorporated into comets, asteroids, and eventually planets. The implications are profound. If amino acids, sugars, and nucleobases are abundant throughout the galaxy, then the emergence of life may be less about a miraculous sequence of accidents and more about the right environment to activate the chemistry that is already present. Planets like Earth, with liquid water, moderate temperatures, and stable atmospheres, act as incubators where these pre-existing ingredients can assemble into self-replicating systems, setting the stage for evolution and eventually complex life. It's as if the universe itself is predisposed to creating the chemical foundations of biology. This widespread distribution of organics also strengthens the plausibility of panspermia. If amino acids, sugars, and nucleobases are everywhere, it becomes easier to envision them being transported between worlds. A rock ejected from Mars, carrying glycine or adenine, could land on Earth, delivering the precise molecules needed to kickstart biochemistry. Comets and asteroids act as natural delivery vehicles, traversing interplanetary distances and sometimes even interstellar space, while protecting fragile molecules within their icy cores or rocky interiors. Over millions of years, this slow but steady rain of organic rich material could provide countless opportunities for life to take root on receptive planets. Interestingly, these discoveries also suggest that life in the universe might share a common chemical heritage. If amino acids, sugars, and nucleobases are ubiquitous, then life emerging on different planets may start with similar molecular tools. While the environment and evolutionary paths may differ, the fundamental chemistry could be strikingly familiar. This opens a door to a tantalizing possibility. Life elsewhere in the universe might be related to life on Earth, connected by the cosmic dispersal of molecules and perhaps even microbial life. Laboratory simulations further reinforce this concept. Experiments mimicking the conditions of space and cometary ice have demonstrated that ultraviolet radiation, cosmic ray exposure, and thermal cycling can synthesize amino acids, sugars, and nucleobases from simple starting compounds like water, methane, and ammonia. This suggests that organic molecules are not only widespread, but can also form naturally in a variety of cosmic environments. Life, or at least its essential components, is thus not restricted to planets, it's a feature of the universe itself. Taken together, these findings radically shift how we view Earth and our origins. Rather than being a unique cradle of life, Earth may be more accurately seen as a recipient of materials already primed for biology. The ingredients for life were available long before humans evolved, long before multicellular organisms walked the oceans, and perhaps long before Mars or other planets developed the conditions for biology. By studying the cosmic distribution of organics, scientists are beginning to trace the threads of a universal chemical network, one in which Earth is just one node in a vast interconnected web of life-ready molecules. This cosmic perspective sets the stage for a deeper understanding of how life might travel not only as molecules, but also as fully functional organisms or microbial spores. The next step in this story is understanding the mechanisms by which these molecules and microbes could move from one world to another, the physical process that connects the chemistry we see in space to the emergence of life on planets capable of sustaining it. This is where the concept of lithopanspermia comes into play, showing how life could literally hitch a ride on rocks traveling through space, bridging worlds across time and distance. The universe, as vast and empty as it may seem, is surprisingly interconnected when it comes to the movement of matter, and with it, the potential movement of life. One of the most intriguing mechanisms by which life could travel between worlds is a process known as lithopanspermia. The term comes from the Greek lithos, meaning rock, and pan, meaning all, literally rock seed everywhere. The idea is deceptively simple. A large asteroid or comet collides with the planet, ejecting fragments of rock into space, some of which may harbor resilient microbes or organic molecules. Over time, these rocks drift through space and, occasionally, intersect with the orbit of another planet, ultimately landing and delivering their microscopic cargo.
Imagine a massive asteroid striking the surface of Mars, the impact so powerful that it blasts tons of rock into space. Some fragments are tiny, others as large as a house, all hurtling through the vacuum at tremendous speeds. Within the cracks and pores of these rocks, hardy microorganisms cling to life, protected from radiation and extreme temperatures by the surrounding stone. For millions of years, these fragments float through the solar system, slowly wandering along gravitational currents shaped by the planets and the sun. Some fragments may pass close to Jupiter or other planets, altering their trajectory before finally intersecting with Earth's orbit. As a fragment plunges through Earth's atmosphere, the outer surface burns, leaving behind a fusion crust, but inside, microbial stowaways survive, ready to seed life in new soil, water, or even icy lakes. Over time, these microorganisms could spread, evolve, and diversify, forming the foundation for ecosystems and eventually more complex life. Lithopanspermia not only explains the potential movement of life between planets within our solar system, but also opens the door to a broader galactic perspective. If rocks can travel between planets, it is conceivable that they could, under rare circumstances, be ejected from one star system and reach another, a process known as interstellar panspermia. While the odds are lower due to the immense distances and timescales involved, the survival of hardy microbes for millions of years, coupled with gravitational slingshots from planetary systems, suggests that even this distant transfer is not beyond the realm of possibility. This process reframes our understanding of life's potential ubiquity. Life doesn't need to emerge independently on every planet. Once it exists, it can propagate naturally through the cosmos, seeding worlds wherever conditions allow. In essence, the universe itself becomes a gardener, scattering life across planets and star systems, each collision and fragment serving as a delivery vehicle for biology. Earth, then, may not be the singular origin point for life, but a recipient of a wider, cosmic network of biological exchange. Lithopanspermia also offers a fascinating bridge back to the question of ancient civilizations. If life can travel from world to world and establish itself elsewhere, then the timeline for intelligence and civilization may extend far beyond what we see on Earth. A planet seeded early could evolve complex life long before humans appeared, giving rise to intelligent species whose traces might vanish over geological time. Impacts, mass extinctions, and planetary upheavals could erase their cities and technology, but the biological lineage, perhaps carried across the stars, would persist, linking distant civilizations across time and space. By connecting the survival of extremophiles, the chemical richness of meteorites, and the mechanisms of lithopanspermia, we begin to see a universe in which life is not isolated, fragile, or random. Instead, it is mobile, resilient, and capable of spreading wherever conditions permit. The cosmos is not a sterile void, but a network of potential life-bearing worlds connected through the movement of rocks, ice, and the molecules they carry. Each asteroid impact, each comet strike, becomes not just a catastrophic event, but a potential opportunity, a delivery vehicle linking distant planets, and perhaps enabling civilizations long before humanity walked the Earth. And if life can travel and survive in this way, it raises profound implications for our understanding of Earth's origins. Perhaps our planet was not the birthplace of life, but simply a recipient of an ancient cosmic inheritance, a world where pre-existing microbes and organic molecules found fertile ground to flourish. This realization sets the stage for contemplating how early life, potentially delivered from space, could eventually give rise to advanced civilizations, and whether intelligence itself might have emerged long before humans. If life on Earth did not originate here, but instead arrived via comets, asteroids, or meteorites, the implications for our understanding of biology, evolution, and even human history are profound.
We tend to think of life as something that emerged locally, uniquely, and sequentially, a product of Earth's chemical soup forming under just the right conditions. But if panspermia is correct, life's origins are no longer confined to our planet. Instead, we are participants in a much broader, older, and more interconnected cosmic lineage. The microorganisms that first arrived on Earth may have traveled for millions, perhaps even billions of years before finding a hospitable environment here, linking us to a biological history that predates the formation of our solar system itself. This idea repositions Earth in the universe. Instead of being the singular cradle of life, our planet becomes a receptive node in a vast interstellar network of life-bearing worlds. Life is no longer a rare accident restricted to a single world, but a process that occurs wherever the chemical prerequisites exist and conditions permit. The organic molecules discovered on comets, the amino acids embedded in meteorites, and the hardy extremophiles capable of surviving space travel all suggest that life may be a common cosmic phenomenon, dispersed and recycled across planets. Earth, in this sense, is not the starting point of biology, but a way station, a place where life took root and diversified.
If life truly arrived from elsewhere, it also challenges how we think about evolutionary timelines. The first microorganisms on Earth, appearing some 3.5 to 4 billion years ago, might not represent the genesis of life, but rather a continuation of a pre-existing lineage. Life on Earth could be the continuation of a story that began in a different star system, carried on particles of rock and ice traveling across the solar system, or perhaps even between galaxies. This possibility drastically extends the age of life, transforming our understanding of biology from a strictly planetary phenomenon to a universal one. Every cell, every gene, every evolutionary adaptation could trace its ancestry not only to earthly conditions, but to a much older interstellar heritage. From a philosophical perspective, this also changes our view of human uniqueness. We like to think of ourselves as the pinnacle of a uniquely earthly evolutionary trajectory, but if life itself is older and more widespread, then humanity is not the first intelligent expression of biology, nor necessarily unique in the cosmos. Our existence may be one link in a chain that stretches across star systems, perhaps even connecting with other intelligent species that arose elsewhere from the same interstellar seed. Life may not be an isolated phenomenon. It could be a pattern replicated throughout the galaxy, governed by universal chemistry and the resilience of microorganisms. This perspective also forces us to reconsider the very definition of origin. Instead of asking where life started, we might ask when life began, recognizing that the true beginning may be impossible to pinpoint because it precedes Earth entirely. Our planet's earliest microbes, then, are not the originators, but inheritors. Every biological lineage on Earth, from bacteria to humans, is descended from organisms that may have evolved elsewhere first. Even the DNA within ourselves could represent the product of a lineage that extends far beyond the temporal and spatial confines of our solar system. Moreover, this perspective has practical implications for modern science. If Earth is part of a cosmic network of life, then searching for extraterrestrial life becomes not a matter of hoping for an independent genesis, but a question of tracing the threads of a shared biological heritage. Life on Mars, Europa, or Enceladus might share common building blocks or even genetic material with life on Earth, making these worlds not just potential sites of independent evolution, but relatives in a cosmic family tree. Understanding the similarities and differences between Earth life and potential extraterrestrial life could reveal the mechanisms by which life propagates, survives, and evolves across vast distances. The implications of a cosmic origin for life also extend to the way we think about our future. If life has successfully traveled through the cosmos in the past, perhaps humanity can participate in a similar process, intentionally spreading life beyond Earth through the colonization of other planets, the deliberate seeding of extraterrestrial environments, or even by protecting and transporting microbial life into space. The resilience and mobility that allowed life to survive interplanetary travel in the past could inform strategies for ensuring its survival over cosmic timescales. Ultimately, the idea that life came from space elevates the story of Earth from a purely terrestrial narrative to a cosmic saga. We are not just the product of local chemistry or random chance, we are participants in a lineage that may stretch across millions of light years, linking our biology to the vast web of stars, planets, and asteroids in our galaxy. Our cells, our genes, and even the potential for intelligence may all be echoes of an older interstellar process that seeded life wherever conditions allowed. And if life is older and more widespread than we imagined, it naturally leads us to the next question. If biology can travel and survive in this way, then could intelligence, the capacity for civilizations and technology, also have arisen elsewhere long before humans ever appeared? Could there have been advanced beings who evolved from earlier waves of life, shaping planets, technologies, or societies that vanished before we ever appeared? If life on Earth, or elsewhere in the solar system, arrived early enough and had billions of years to evolve, it is not unreasonable to speculate that advanced civilizations could have existed long before humans ever appeared. The idea stretches the imagination, but when framed in terms of timescales and probability, it becomes a scientifically grounded thought experiment rather than pure fantasy. The Earth is approximately 4.5 billion years old, with microbial life appearing as early as 3.5 to 4 billion years ago. Humans, by contrast, occupy an incredibly brief window, a few 100,000 years at most. That leaves an almost incomprehensibly long period during which other intelligent, technologically capable species could have evolved, flourished, and disappeared without leaving a clear trace. This notion becomes even more compelling when combined with the idea of panspermia. If life did not originate on Earth, but arrived fully or partially developed from another planet, the biological timeline for Earth's ecosystems may have started even earlier than previously thought. Life could have had a head start of hundreds of millions or even billions of years compared to the evolutionary path we know. In such a scenario, the emergence of intelligence could have occurred multiple times in parallel or sequentially, giving rise to advanced civilizations whose remnants may now be lost to the relentless forces of geology and time. The possibility of pre-human civilizations is of course constrained by evidence, or rather the lack of it. Geological processes like erosion, subduction, volcanism, and continental drift are incredibly effective at erasing structures and artifacts over tens to hundreds of millions of years. Any cities, roads, or technology that existed in such a distant past would likely have been destroyed or recycled into the planet's crust. Even large-scale industrial activity might only leave faint chemical or isotopic traces, perhaps detectable only by highly sensitive geochemical analysis. This is precisely the type of scenario the Silurian Hypothesis seeks to explore. What signatures of a vanished civilization might survive the eons, and how might we detect them? Speculation about advanced pre-human civilizations also invites questions about the nature of intelligence and technological development. If life has billions of years to experiment, evolution may produce intelligent species in forms very different from us. They may not have used metal tools, built cities, or followed the same developmental trajectory as humans. Instead, their intelligence might have been expressed in alternative ways. Complex communication networks, biochemical technology, or even subterranean or oceanic societies that leave minimal traces on the surface. The diversity of life's potential makes it difficult to predict how such a civilization might appear in the geological record, or whether we would even recognize it. Cosmic context further expands this possibility. If life can travel between planets via lithopanspermia, then Earth could have been seeded multiple times over its history, potentially introducing entirely different branches of intelligent life at various points. Life on other planets in our solar system or nearby star systems might have produced intelligent species whose civilizations predate humanity by millions of years. Even without interstellar travel, the sheer age of the galaxy allows for numerous opportunities for advanced civilizations to arise, flourish, and vanish long before humans evolved on Earth. The universe may be a succession of intelligences, appearing and disappearing in cycles across time and space, with only faint biological echoes left behind. This perspective also challenges anthropocentric assumptions. Humans tend to view ourselves as the first, or at least the most advanced civilization to have existed. But in a universe measured in billions of years, the odds suggest otherwise. The emergence of intelligent life is not necessarily rare. It is a consequence of evolutionary time and favorable conditions. If microorganisms could seed a planet, survive, and evolve over vast epochs, then intelligence could plausibly arise long before humans, only to vanish in the face of planetary catastrophes, climate shifts, or self-destruction. Extinction events, from asteroid impacts to supervolcanoes and ice ages, could erase all evidence of a civilization that lasted for millennia, leaving no more trace than a faint isotopic anomaly in ancient rocks. While the idea is highly speculative, it is anchored in scientific reasoning. We know Earth has experienced multiple mass extinctions and environmental upheavals. We know life is resilient, capable of surviving and adapting over billions of years. We know the fossil and geological records are incomplete, with enormous stretches of time represented by only sparse layers of sediment. Taken together, these facts suggest that the absence of evidence is not evidence of absence. The possibility of pre-human intelligence is not ruled out by science. It is simply constrained by what we have been able to detect so far. This line of thought inevitably leads to an even broader consideration: the cyclical nature of intelligence and civilization in the universe. Perhaps the rise and fall of civilizations is a natural process, occurring repeatedly wherever life is sufficiently advanced. Humanity might be just the latest iteration in a cosmic pattern, a civilization appearing temporarily in a vast timeline filled with others that came before, and potentially others that will follow. The implication is humbling. Intelligence may be less about permanence and more about transient emergence, a phenomenon that flickers briefly in the cosmic tapestry before being erased by time, space, and planetary processes. If we accept this possibility, the search for extraterrestrial intelligence gains a new dimension. We might not be seeking civilizations that exist today, but evidence of civilizations that existed millions or even billions of years ago. This will shift our approach from detecting active signals to identifying subtle markers in planetary geology or atmospheric chemistry, traces of technological activity preserved faintly in the vastness of space and time. Understanding how early life and potentially early intelligence could propagate across planets prepares us to recognize these markers and expands the scope of our exploration beyond our own species' narrow window of existence. In essence, contemplating pre-human advanced civilizations encourages us to view life, intelligence, and civilization on Earth as part of a continuum that may extend far deeper into the past than our current records suggest. It invites us to consider not just the fragility of human existence, but the impermanence of intelligence itself, framed within a cosmos where life has had billions of years to experiment, diversify, and perhaps produce civilizations that vanished long before we arrived. The tantalizing possibility of advanced civilizations existing long before humans is inevitably intertwined with the harsh realities of Earth's history. Our planet is not a stable, unchanging environment. It is a dynamic, violent, and often catastrophic world. For billions of years, life on Earth has been subjected to events of such magnitude that they have reshaped ecosystems, extinguished species, and even altered the very chemistry of the atmosphere. If a civilization had existed millions or hundreds of millions of years ago, it would have faced these same challenges, and in all likelihood, some of them would have been existential threats, capable of erasing nearly all physical evidence of their existence.
One of the most dramatic examples of global catastrophe is asteroid or comet impacts. The most famous of these, the Chicxulub impact event 66 million years ago, is widely believed to have triggered the mass extinction that wiped out the non-avian dinosaurs. A single celestial body, traveling at tens of kilometers per second, collided with Earth with the force of billions of nuclear explosions. The impact would have triggered immediate devastation over thousands of kilometers, followed by a nuclear winter effect. Dust and aerosols thrown into the atmosphere would have blocked sunlight, drastically lowering global temperatures, collapsing food chains, and causing widespread extinction. Any civilizations present at the time, particularly those on the surface, could have been obliterated or forced into such desperate survival conditions that their technology and culture would leave virtually no trace. Volcanism is another cataclysmic force with the power to alter planetary habitability. Large igneous provinces, such as the Siberian Traps, released enormous volumes of lava, sulfur dioxide, and greenhouse gases over millions of years, triggering climate changes that caused mass extinctions. These eruptions can acidify oceans, poison the atmosphere, and eliminate habitats across entire continents. Even if intelligent species possessed advanced technology, prolonged volcanic activity on this scale could decimate populations, destroy infrastructure, and leave geological layers filled only with lava flows and ash, materials in which most artificial constructs would be quickly obliterated. Ice ages, too, have repeatedly transformed the face of Earth. During periods of extreme glaciation, vast portions of the planet's surface were buried under kilometers of ice, obliterating ecosystems and altering sea levels drastically. Entire continents were reshaped. Coastlines, river systems, and fertile plains were erased or relocated. A civilization thriving during one of these glacial maxima could have seen its cities buried under ice or swept away by glacial movement. When the ice eventually receded, geological activity would have continued to reshape the landscape, leaving little more than subtle chemical or isotopic signatures as potential evidence of their presence. Even relatively smaller-scale catastrophes, such as mega tsunamis, earthquakes, or shifts in magnetic poles, could contribute to the erasure of evidence. Over millions of years, the constant recycling of the Earth's crust, through tectonic activity, subduction, and erosion, removes most traces of surface structures. Cities, roads, monuments, and even industrial complexes would eventually be reduced to fragments and buried beneath layers of sediment, lava, or ice, or be chemically altered beyond recognition. In essence, the Earth is an artist, constantly painting over its own history, preserving only the most durable chemical or mineral markers while erasing the majority of physical evidence. It is worth noting that mass extinctions and planetary upheavals do not need to completely annihilate life to erase a civilization. Even if a species survived in small numbers, reduced to isolated pockets or underground refuges, the collapse of infrastructure, loss of technological knowledge, and absence of durable written records could effectively erase their cultural legacy. Life might persist biologically while leaving almost no technological footprint. Geological time would then hide the existence of intelligent species as completely as it hides countless extinct microbial and multicellular organisms whose fossils never formed or were destroyed. Considering these global catastrophes, it becomes clear why the Silurian hypothesis emphasizes indirect evidence, anomalies in isotopic ratios, unusual concentrations of synthetic compounds, or subtle chemical footprints preserved in deep strata. Even if a civilization that had mastered advanced technology and industry could leave barely detectable traces if the Earth's natural forces were allowed millions of years to act. A combination of asteroid impacts, volcanic eruptions, ice ages, and tectonic recycling could plausibly erase almost all evidence, leaving only whispers of its existence in the geological record. This realization also frames our understanding of human vulnerability. If civilizations can be wiped out by catastrophic events, even advanced ones, then humanity itself is a temporary occupant on a planet with a volatile history. Extinction events in the past likely reset the stage multiple times, allowing life to evolve anew and civilizations to rise and fall long before humans arrived. From this perspective, the Earth may have witnessed multiple iterations of intelligent life, each potentially obliterated by natural forces that are indifferent to complexity or achievement. The broader implication is profound. The absence of direct evidence of pre-human civilizations is not evidence that they never existed. The combination of massive planetary catastrophes and the Earth's continuous geological processes makes it plausible that advanced species could have risen and vanished without leaving discernible surface traces. Life itself, resilient as extremophiles demonstrate, might survive and evolve repeatedly, but the civilizations it produces, vulnerable to planetary-scale disasters,
could leave behind nothing but subtle geochemical anomalies buried deep in rock formations.
Understanding ancient global catastrophes gives us a framework for interpreting the gaps in the fossil and archaeological records. It helps explain why, even if intelligent life existed millions of years ago, we might detect only indirect evidence. Isotopic shifts, unusual concentrations of long-lived synthetic compounds, or other chemical signatures in strata far older than any known human activity. These natural events act as both erasers and record keepers. They destroy most evidence of life's complex achievements while simultaneously embedding subtle chemical fingerprints that, if carefully analyzed, could reveal traces of the past. By appreciating the scale and frequency of these planetary catastrophes, we gain a sense of how fragile civilizations are and how easily their existence could vanish from the geological record. It also sets the stage for our next discussion. Where and how might we detect such hidden evidence? What anomalies or clues in the rocks, ice, and sediments of ancient Earth might point towards civilizations that lived long before humans? If we accept the possibility that advanced civilizations may have existed long before humans, the next natural question is, how would we detect them? Given the immense spans of geological time, the vast majority of physical structures, buildings, roads, machines, would have been obliterated by erosion, tectonic activity, and chemical degradation. However, Earth has a remarkable capacity to record events in more subtle ways. Deep within its rocks, ice cores, and sediment layers, there may exist indirect evidence, traces that hint at unnatural activity or advanced technology long erased from the surface. Scientists exploring these possibilities look for anomalies that could survive the ravages of millions or even billions of years. One potential avenue is the study of isotope ratios. Chemical elements come in different isotopes, atoms of the same element with differing numbers of neutrons, and certain industrial processes can alter the natural abundance of these isotopes. For example, nuclear reactions or large-scale chemical manufacturing could leave traces detectable long after all physical structures have vanished. Anomalous concentrations of isotopes like carbon-13 or nitrogen-15, especially in ratios inconsistent with natural processes, could indicate the presence of past biological or technological activity. Even isotopes like plutonium-244 or other long-lived radioisotopes, which are rare in nature, could serve as markers of ancient technological activity if they are found in unexpected strata. Another potential clue lies in synthetic materials that are highly resistant to decay. Plastics, polymers, and certain alloys might not survive unchanged over millions of years, but some chemical signatures of industrial compounds could persist. For instance, long-chain hydrocarbons, chlorofluorocarbons, or other industrially produced molecules could become trapped in sediment layers or fossilized in mineral matrices, leaving chemical fingerprints that do not match any known natural processes. These molecules would stand out as anomalies in very ancient strata, potentially signaling the presence of advanced life and technology that existed long before humans. Fossilized microstructures may also hold answers. Just as meteorites like ALH 84001 contain microscopic formations that resemble microbial fossils, ancient Earth rocks could preserve unusual patterns inconsistent with natural geological or biological processes. Tiny, highly ordered metallic or ceramic structures embedded in ancient rock layers, far older than the human timeline, could hint at technological activity. While this evidence would be difficult to interpret conclusively, it would be precisely the kind of subtle trace that could survive the relentless transformations of the Earth's surface. Even subtle chemical anomalies could provide hints. Certain elements or compounds such as rare earth metals, synthesized isotopes, or unusual organic molecules may indicate high-temperature industrial activity or advanced chemistry that natural processes would not produce. These could appear in sediments, mineral deposits, or fossilized ocean beds. Over millions of years, while structures collapse and organic matter decays, the chemical signatures of large-scale technological processes could persist, frozen in geological memory. Scientists also examine microstratigraphy, the study of fine layers of sediments and rock, for clues. Changes in mineral composition, sudden introductions of foreign materials, or abrupt isotopic shifts might reveal disruptions inconsistent with natural processes. These anomalies could signal the rise and fall of a pre-human civilization, especially if they coincide with other global events, such as mass extinction layers, unusual climate shifts, or geologically rapid changes in ocean chemistry. A civilization might not leave skyscrapers or satellites, but it could leave traces in the very chemistry of the Earth itself, hidden in plain sight if we know how to look. Even ocean sediments hold potential clues. Deep-sea cores accumulate slowly over millions of years, often preserving chemical and biological signals from extinct ecosystems. Layers containing unusual concentrations of metals, synthetic molecules, or isotopic anomalies could correspond to periods of advanced industrial activity. Similarly, ice cores from polar regions trap atmospheric gases and aerosols that reflect the chemical composition of past atmospheres. In theory, ancient civilizations, if they existed, could leave faint but detectable traces in these archives, subtle markers of activities that altered the planet in ways not easily erased. Searching for such evidence requires a combination of disciplines: geology, chemistry, paleontology, and even archaeology applied on a precedented temporal scale. Unlike conventional archaeology, which examines thousands of years, this endeavor extends to millions or billions of years, requiring an understanding of how chemical and physical markers degrade, migrate, or transform over geological time. Researchers would need to distinguish between natural anomalies, like volcanic activity or asteroid impacts, and potential signals of intelligent intervention. It's a painstaking process, but one that could, in principle, reveal hidden chapters of Earth's history that conventional study has overlooked.
The concept of hidden evidence also underscores the fragility of civilizations. Even technologically advanced societies may leave little trace over deep time, surviving only in the most resilient forms. Isotopic signatures, durable synthetic molecules, or subtle anomalies embedded in rocks. Earth's dynamic systems erase almost everything else, meaning that any civilization preceding humans might be detectable only through indirect chemical or structural clues, rather than obvious ruins. This understanding helps frame our perspective. Absence of evidence is not evidence of absence. The clues may exist, but they are hidden deep in the geological record, waiting to be discovered with careful, imaginative, and rigorous analysis. These considerations naturally lead us to the broader scientific and philosophical context. Why, despite the tantalizing possibilities, most scientists remain skeptical, and what this debate tells us about our place in the cosmos. If the traces of past civilizations are so subtle and easily erased, then extraordinary claims must be met with extraordinary standards of evidence. Yet even in the absence of definitive proof, the pursuit of hidden geological evidence encourages us to expand our imagination, refine our scientific tools, and contemplate the vast timeline of life and intelligence on Earth, one that might be far older and more complex than we have ever considered. The notion that advanced civilizations may have existed long before humans is undeniably fascinating, but it exists on the boundary between speculation and empirical science. While the idea is theoretically plausible, it faces a fundamental challenge: the absence of concrete evidence. Most scientists approach the concept with cautious skepticism, not because they believe it is impossible, but because, so far, there are no definitive markers in the geological, chemical, or fossil record that unambiguously point to pre-human intelligent life. Science, by its nature, demands evidence that can be tested, reproduced, and critically examined. Without such evidence, even the most elegant or compelling hypothesis remains speculative. The scientific principle often invoked here is that extraordinary claims require extraordinary proof, a standard made famous by astronomer Carl Sagan. The idea of civilizations preceding humans qualifies as extraordinary because it would fundamentally rewrite our understanding of Earth's history, life's evolution, and the uniqueness of human intelligence. It challenges centuries of assumptions about chronology, the pace of evolution, and the fragility of biospheres. Because of its profound implications, scientists cannot accept it lightly. The burden of proof rests squarely on the hypothesis. Any proposed evidence, isotopic shifts, unusual molecular signatures, or fossil microstructures must be scrutinized rigorously to ensure it cannot be explained by natural processes, which are overwhelmingly abundant and diverse.
Skepticism also stems from the tremendous difficulty of detection. Earth's geological processes are relentless, recycling crust, eroding surfaces, and reshaping environments over millions of years. Even human civilizations which have produced cities, roads, and durable materials like concrete and metal leave traces that may vanish or become unrecognizable over deep time. Extrapolate that into a scale of tens or hundreds of millions of years, and the challenge becomes almost insurmountable. Tectonic activity, volcanic eruptions, glaciations, and erosion would erase most physical artifacts, leaving only subtle chemical or isotopic traces, if anything. Detecting such evidence requires tools and methods that are still in developmental stages, which adds to the understandable skepticism of the scientific community. Furthermore, natural processes often produce anomalies that mimic artificial ones, making interpretations precarious. Isotopic shifts can arise from volcanic activity, asteroid impacts, or changes in the biosphere. Unusual molecular signatures could result from complex prebiotic chemistry or geochemical processes, rather than industry or technology. In the absence of corroborating evidence, it is easy for researchers to misinterpret natural signals as potential markers of intelligent activity. This is a classic problem in science. When extraordinary possibilities are proposed, extraordinary rigor is required to separate genuine anomalies from natural noise.
Yet the scientific community does not dismiss the idea out of hand. Rather, it treats it as a fascinating but unverified hypothesis, worthy of careful thought and investigation. Researchers may explore isotopic ratios in deep strata, study long-lived synthetic molecules, or re-examine fossil microstructures, always applying a critical lens. The hypothesis forces us to consider the limitations of the geological record, the resilience of life, and the possibility that intelligence, once emerged, might be ephemeral, leaving minimal traces. It expands the conceptual horizon of science, challenging researchers to refine methods, push observational boundaries, and consider timescales far beyond conventional archaeological or paleontological studies. Another reason scientists remain cautious is that confirming pre-human civilizations would require cross-disciplinary convergence of evidence. Geology, chemistry, paleontology, planetary science, and even astrobiology would need to align to support the claim. A single anomaly in isolation, say a peculiar isotope ratio or unusual mineral deposit, is insufficient. Only when multiple lines of independent, reproducible evidence point in the same direction could the hypothesis gain credibility. Until then, it remains an intriguing intellectual exercise, a what-if that encourages creative exploration while respecting the standards of scientific rigor. This tension between plausibility and proof illustrates a core principle of science: openness to possibilities tempered by skepticism. The notion of pre-human civilization stretches imagination and invites bold questions, but science demands that those questions be answered with evidence, not speculation. The idea is neither absurd nor impossible. It is simply unproven. Its extraordinary nature requires extraordinary scrutiny, rigorous methodology, and patience, particularly when examining traces that may have been buried, altered, or erased over hundreds of millions of years. Interestingly, the very act of considering pre-human civilizations can inspire new scientific investigations. By imagining what indirect markers might survive deep time, isotopic anomalies, chemical residues, fossilized microstructures, researchers develop innovative techniques for detecting subtle signals. Even if no pre-human civilization is ever confirmed, these methods enrich our understanding of Earth's history, the resilience of life, and the processes by which ecosystems and biospheres evolve over vast temporal scales. In other words, the exploration itself advances science, regardless of the final answer. Ultimately, the scientific community's skepticism reflects both prudence and respect for evidence. Extraordinary claims, especially those that could overturn our understanding of life's timeline and humanity's place in the universe, must withstand rigorous testing.
Until such evidence is found, the idea of pre-human civilizations remains a speculative but stimulating hypothesis, a reminder that our planet's history may be far more complex, mysterious, and layered than we currently understand. From this perspective, considering ancient civilizations or panspermia doesn't just challenge science, it expands our cosmic imagination. It encourages us to think beyond the narrow confines of human history, to explore the broader context of life in the universe, and to ponder whether intelligence is a rare anomaly or a recurring transient feature of life. These reflections naturally lead us to the bigger picture, the cosmic perspective that situates Earth and humanity within a vast, interconnected universe. If we zoom out from the surface of Earth and consider the universe on a grander scale, the implications of panspermia and the possibility of pre-human civilizations become breathtakingly profound. Instead of seeing life as an isolated phenomenon confined to the tiny blue dot we call home, we can begin to imagine it as a cosmic network, a vast web of biological connections stretching across the galaxy and perhaps even beyond. Every planet, comet, and asteroid with the right conditions becomes a potential node in this network, capable of receiving and distributing life through processes like lithopanspermia. In this view, life is not localized, but interlinked, a sprawling interstellar family tree with roots that may extend far beyond our solar system.
Panspermia suggests that the emergence of life is not unique to Earth, but that Earth itself could have been seeded by life that originated elsewhere. If microbial life or organic molecules arrived from distant worlds, then our biology might carry chemical and genetic signatures that trace back to other planets, or even other star systems. Every cell in our body, every gene in our DNA, could be part of a much larger, older biological lineage, one that spans not just millions, but billions of years and perhaps multiple worlds. This cosmic perspective transforms our understanding of evolution. It is no longer a strictly local phenomenon, but part of an expansive network in which life is shared, propagated, and perhaps even recycled across planets and solar systems. The idea of a cosmic family tree is compelling because it reframes our relationship with the universe. Humanity is often tempted to see itself as the center of life's story, but panspermia implies that we may be one branch among countless others in a galaxy-spanning tree of life. Microbes that seeded Earth may have traveled from Mars, Venus, or even exoplanets orbiting distant stars. Life on these other worlds, if it exists, could share ancestry with terrestrial organisms, forming a web of biological kinship that links planets across space. Even if intelligent civilizations arose elsewhere long before us, they may have been part of the same lineage of life, diverging in form, thought, and technology, but connected at the most fundamental biological level. Looking at the universe through this lens also reframes how we think about time. The Earth is only 4.5 billion years old, but the galaxy is much older, and life elsewhere could have arisen hundreds of millions or billions of years before our planet even formed. Civilizations could have emerged, flourished, and disappeared elsewhere in the galaxy long before humans existed. Some of the first seeds of life that arrived on Earth may have been delivered from these ancient worlds, making us part of a living legacy that predates our solar system. This perspective challenges our anthropocentric notions of time and significance, placing humanity in a continuum that stretches across space and cosmic history. The interconnectedness implied by panspermia also suggests that life in the universe is resilient and adaptive. If microbes can survive the journey between planets, protected in rocks or ice, then life can withstand the harshness of space and the violent upheavals of planetary environments. This mobility of life increases the probability that life is widespread, not confined to isolated pockets. Each planet may be both a recipient and a donor, constantly exchanging biological material over millions of years. In this sense, life itself becomes a unifying force in the cosmos, linking otherwise distant and seemingly separate worlds through a shared biological heritage. A cosmic perspective also provides context for intelligence.
If life is mobile and persistent, then the potential for intelligence may arise in multiple locations over time. Civilizations may have appeared, evolved, and vanished on planets we will never see, leaving only subtle traces behind. Even if humans are the first intelligent species to document technology and knowledge on Earth, we might not be the first in the galaxy. Panspermia implies that intelligence, like life itself, could be a recurring pattern in the universe, emerging wherever conditions permit and disappearing when circumstances become unfavorable. The stars, in essence, are laboratories where biology experiments with life in countless iterations, some of which may evolve consciousness and civilizations that we can only speculate about. Furthermore, this perspective invites a redefinition of ancestry and kinship. If life is shared across the cosmos, then our biological relatives may not be limited to Earth. Microbes, plants, or even animals on distant planets could share chemical or genetic heritage with us. The DNA within our cells might not be purely terrestrial in origin, but a chapter in a galaxy-wide story. Life becomes a cosmic continuum, a network of living systems connected across unimaginable distances in deep time, reinforcing the idea that the universe itself is not empty, but teeming with interconnected biological potential. Philosophically, this cosmic view challenges human exceptionalism. We are not the first, and likely will not be the last intelligent life in the universe. Our story is one chapter in a vast, multiplanetary saga of life that stretches across eons and light years. The survival of extremophiles, the chemical richness of meteorites, the mobility of life via lithopanspermia, and the possibility of ancient civilizations all converge to suggest that life is not an accident, but a cosmic phenomenon, one that binds us to distant worlds, ancient histories, and perhaps to civilizations that have risen and fallen before humanity ever appeared. From the practical standpoint, embracing a cosmic perspective transforms the way we search for life beyond Earth. Instead of asking whether life exists elsewhere independently, we begin to ask whether life on other worlds is related to us, part of the same cosmic lineage. It expands our search from a quest for isolated phenomena to a study of interconnected life systems potentially linked by shared chemistry, genetics, and evolutionary pathways. This perspective also inspires humility and curiosity, reminding us that Earth is not an isolated cradle, but a single node in a vast, dynamic, and interconnected biosphere that spans the universe. As we consider this broader cosmic perspective, it naturally leads to profound philosophical reflections. If life is indeed part of a shared galactic network, what does it mean for identity, for legacy, and for the significance of intelligence? Are civilizations like ours fleeting sparks in an ongoing cosmic experiment, or are they part of a repeating pattern in which life, intelligence, and perhaps even consciousness arise, vanish, and emerge again? These questions point to a profound truth. The story of life is far grander and more interconnected than we have ever imagined.
From the cosmic web of life, it is a small but important step to ponder not just biological connections, but the deeper philosophical and existential implications. How our understanding of life, intelligence, and civilization changes when we see ourselves as one branch of a universal family tree rather than the center of existence. This naturally brings us to the next consideration: the philosophical implications of being part of a universe where life and intelligence may have appeared repeatedly, disappeared, and re-emerged, weaving a pattern that transcends any single planet or species. If we allow ourselves to truly absorb the idea that life on Earth might not be an isolated miracle, but rather part of a vast interplanetary, perhaps even interstellar continuum, then a deep philosophical shift begins to unfold. Suddenly, the story of humanity transforms from a singular narrative into one chapter within a cosmic epic billions of years long. The atoms that make up our bodies may have traveled through ancient worlds, formed the structures of long-lost life, and been recycled through time to eventually become part of us. If panspermia and the possibility of pre-human civilizations are both real, then we are not the beginning. We are a continuation.
We are inheritors of a biological and perhaps even intellectual legacy that stretches across deep time and space, connecting us not only to the creatures of Earth's past, but also to possible intelligences that may have walked on other worlds, pondered similar questions, and vanished into cosmic silence. This notion carries profound implications for how we understand existence. If intelligence is not unique to humanity, if it has appeared before and will appear again, both on Earth and elsewhere, then intelligence itself may be a kind of universal phenomenon, an emergent property of life wherever it takes root. In that sense, consciousness may not belong to us. It may belong to the cosmos. We, as thinking beings, could be the universe's way of perceiving itself for a brief moment before passing that awareness onward, like a flame handed through eternity. The awareness that we think becomes not a sign of human dominance, but of cosmic participation. If life and intelligence are cyclical, arising, thriving, and disappearing again and again, it reframes the idea of permanence. Civilizations might rise, achieve brilliance, and then collapse, their traces swallowed by geological time or galactic distance. Yet each emergence of intelligence could be seen as part of a repeating pattern, a rhythm embedded within the fabric of the cosmos. Perhaps intelligence is less an endpoint and more a recurring event, like stars igniting and burning out, or galaxies colliding and reforming. If that is true, then the universe itself is not static, but alive. A dynamic system in which consciousness and creativity continually emerge from the fertile soil of matter and energy. Such a perspective can be both humbling and empowering. On one hand, it diminishes the anthropocentric idea that humanity is special or alone. We are likely not the pinnacle of creation, but rather one expression of a universal tendency toward complexity and awareness. On the other hand, this perspective magnifies our connection to the cosmos. To think, to wonder, to build and destroy, to love and fear, all of these are not merely human experiences, but cosmic ones, patterns repeated in different forms across space and time. Every thought we have might echo the thoughts of beings long gone, their civilizations erased, but their essence carried forward in the continuity of life. If panspermia and the possibility of pre-human civilizations are both real, then we are not the beginning. We are a continuation. We are inheritors of a biological and perhaps even intellectual legacy that stretches across deep time and space, connecting us not only to the creatures of Earth's past, but also to possible intelligences that may have walked on other worlds, pondered similar questions, and vanished into cosmic silence. This realization also forces us to confront our own fragility. If civilizations can rise and fall, if intelligence can emerge and then vanish, then humanity too may be temporary. The traces of our technology, art, and thought may not endure. One day the continents will shift, the oceans will rise or disappear, and the monuments of our time will crumble into dust. Just as we search for hints of ancient life in rocks and meteorites, perhaps some future intelligence, human or otherwise, will one day seek traces of us. The thought is sobering. All our achievements, our dreams, our digital records may be but a whisper in the grand timeline of the universe. But that impermanence is not tragic. It is beautiful. It connects us to every form of life that has ever existed, each one burning brightly for a moment before returning to the cosmic whole.
If intelligence continually arises, it may not be the survival of individual civilizations that matters most, but the continuation of awareness itself. Life, in its endless experimentation, gives rise to consciousness over and over, ensuring that somewhere, somehow, the universe is always aware of itself. Our task, then, is not merely to endure, but to contribute, to add our spark of understanding, creativity, and compassion to this ongoing cosmic process. In doing so, we become co-authors of the universe's own self-discovery. From a philosophical standpoint, this realization also reshapes our sense of ethics and responsibility. If we are part of a shared cosmic lineage, then the way we treat our planet, our fellow beings, and even potential extraterrestrial life becomes a reflection of how we value that lineage. Our actions, whether destructive or nurturing, ripple through the fabric of that interconnected web. Preserving Earth's biosphere is not merely environmental stewardship. It is honoring our ancient cosmic ancestry. To destroy life here would be to break a chain billions of years long, one that perhaps began in the heart of a distant star system and found expression in us. It also invites a deeper sense of unity. If all life shares a common origin, if microbes from Mars or distant exoplanets are our distant relatives, then the divisions we create among ourselves on Earth become trivial in comparison. Race, nationality, and even species distinctions pale before the truth that we are all composed of the same cosmic material, animated by the same spark that has traveled through the universe for eons. The realization that we are literally made of stardust and possibly share ancestry with beings across galaxies dissolves the illusion of separateness. It invites us to see ourselves as part of something vastly larger, a living, evolving cosmos, where every consciousness, no matter how small, plays a role. There's also a quiet, existential beauty in this vision. If civilizations have come and gone before us, and if others will come after, then meaning does not depend on permanence. It exists in the act of participation, in the way life expresses itself, in the brief flowering of awareness that each species and civilization brings into the universe. Meaning is not something bestowed upon us from outside. It is something we create through curiosity, creativity, and compassion to this ongoing cosmic process. We may not endure forever, but our existence is nonetheless significant because it is part of the universe's unfolding story. This cosmic philosophy transforms despair into awe. Instead of mourning our eventual disappearance, we can celebrate our moment within the continuum. We are here now, alive, aware, capable of reflection, and that in itself is extraordinary. If intelligence arises repeatedly throughout time and space, then perhaps the universe itself longs to know and express itself through us. Our thoughts, our questions, even our uncertainties become part of that grand cosmic dialogue. From this reflective understanding emerges a new kind of hope, one that transcends human history and even planetary boundaries. If life and intelligence are woven into the very structure of reality, then we can trust that the story will continue, even if we are not here to witness it. Somewhere, someday, another world may awaken, look up at its stars, and ask the same question we are asking now. Were we the first? And in that moment, the cycle begins again. As this awareness settles, we return full circle to the mystery that started it all. The recognition that perhaps we are not the first civilization, and perhaps we will not be the last. Yet, that realization does not diminish us. It elevates us. It places us within an eternal story of creation, extinction, and renewal, a story that will continue long after we are gone. As we bring this extraordinary exploration to a close, it's impossible not to feel a profound sense of wonder. We have traveled from the surface of Earth to the depths of geological time, from the microscopic resilience of extremophiles to the sweeping scale of the cosmos. And in doing so, we've glimpsed the possibility that life, intelligence, and perhaps civilizations themselves are far older and more widespread than we ever imagined. Every moment we spend pondering these ideas reminds us that the universe is vast, mysterious, and largely unexplored, a stage upon which countless stories may have unfolded long before humans arrived, and countless others will play out long after we are gone. The search for answers, whether through isotopic anomalies, chemical traces, meteorites, or the study of distant exoplanets, is ongoing. Every discovery, from amino acids in comets to microbes surviving in extreme conditions, nudges us closer to understanding the incredible resilience and mobility of life. Even if we never find definitive proof of civilizations predating humanity, the very act of contemplating them expands our imagination, deepens our curiosity, and challenges us to see our planet and species as part of something far greater than ourselves.
Reflecting on the possibility that life has been traveling, evolving, and experimenting across the cosmos for billions of years forces us to reconsider our place in the universe. Are we unique or merely one expression of a recurring pattern of intelligence? Is the story of life on Earth a singular miracle or one chapter in an ongoing interstellar saga? These questions may never have absolute answers, but the beauty lies in the pursuit, in imagining the unimaginable, exploring the undetectable, and pondering our connection to distant worlds, both past and future. Perhaps the most profound takeaway is a sense of humility and continuity. If life has been seeded across worlds, if civilizations can rise and vanish over geological time, then humanity is both fleeting and precious. We are part of a lineage that stretches beyond our planet, linked to a cosmic family of organisms that may have traversed the stars long before we existed. And in that lineage, we find both inspiration and responsibility. To understand, to protect, and to continue the story of life on Earth and beyond. Maybe we're not the first civilization to leave its mark, subtle or otherwise, upon this planet. Maybe intelligence has flickered, arisen, and disappeared countless times before us, leaving only whispers of its existence embedded in the rocks, ice, and sediments of deep time. And maybe, just maybe, we won't be the last. Perhaps somewhere, out there among the stars, new life and intelligence are beginning their own journey, continuing the cosmic chain of which we are a part. In the end, a mystery is what fuels our imagination, drives our science, and connects us to the universe in ways both intimate and infinite. To contemplate life, intelligence, and civilizations beyond our own is not to diminish humanity, but to expand it, to place us in a tapestry that is larger, older, and more magnificent than we could ever fully grasp. So, as we look to the stars tonight, as we study the rocks beneath our feet, and as we reflect on the fleeting yet profound nature of our existence, let us do so with awe and curiosity, because the universe is vast, life is resilient, and intelligence may be more enduring and widespread than we ever dared to dream. Maybe we're not the first, and maybe we won't be the last. The mystery continues, and with it the invitation to explore, imagine, and wonder. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.